Race conditions is an area that I'm going to demonstrate shortly. What race conditions are, generally they're cases where you have two separate threads, two separate ADA tasks, trying to manipulate the same data at potentially the same time. The problem with race conditions is that they don't always happen. So you may have a bug that only shows up now and then, or worst of all, it shows up only when it's at the customer site. So race conditions can be very tricky to find and eliminate by doing testing. What CodePeer does is it does a mathematical analysis to find what are the possible race conditions, the possible places where the same data object might be manipulated by two concurrently running tasks. And it's a much more thorough approach. It isn't catch as catch can, if you will. It catches them all. So now it may, of course, you may say, well, that one's okay because of certain things I know. But CodePeer finds those places that look suspicious. Okay, so at this point, I'm going to stop the slideshow and go into the actual CodePeer tool. And I'll come back and finish up this slideshow at the end. I've started our GPS, our GNAT Programming Studio, and I've opened an old standard test case for showing real-time, or let's say multi-threading programs. In this case, the so-called dining philosophers. Now, some of you may be familiar with it. The basic model is that you have 5 philosophers, and they live for a certain amount of time. And what they do while they're alive is they think and they eat. And they eat spaghetti, let's say, and it's a round table, and they each need 2 forks to eat their spaghetti. But there are only a total of 5 forks and a total of 5 philosophers. So there's definitely a contention for getting 2 forks. And if each of the philosophers sits down and grabs the left fork, then when they go to grab the right fork, they're now waiting for the philosopher to their right, who is waiting for the philosopher to their right, and so on around in a circle, and you have what is sometimes called a deadlock or a deadly embrace, much more exciting way of looking at it. So this is what this program represents. It creates a separate ADA task for each philosopher, starts those ADA tasks running. The ADA tasks in a cyclic mode, they think for a little while, and then they get hungry, they pick up their forks, and they do some eating for some random amount of time, and they put down the forks, and then they wrap around again. So we're going to give CodePeer this chunk of code and say, analyze all. Okay. And off it goes. We can see over in the upper corner here, we have a progress bar. And it's now analyzed our program. And it's going to bring up the CodePeer report. And the CodePeer report gives us the list of the various kinds of issues that have been identified. We have the driver program here, test dining philosophers, which we found 4 problems with at the high level and none at the medium or low level. And in the sort of the main part of the code, the actual algorithm with the various tasks and so on, we found 1 high-ranking problem, 7 medium-ranking problem, and 4 low-ranking problems. And we'll work our way through these. So let's start with the program here with the 4 hard failures, if you will. And we can now look at the source code, and we see that the various lines have been identified with colors. High is red, the medium would be orange, and the low would be yellow. And we can click on one of these and see what CodePeer believes the problem is. It says high, precondition failure due to an array index check. And these are the common weakness enumeration IDs associated with array index checking. So there are a lot of problems in the common weakness enumeration that relate to array index out of bounds. The so-called buffer overflow problem is widely recognized as one of the sources of many issues with programs, particularly those that are trying to be high security. It's often a way to break into a program. So CodePeer goes out of its way to identify those sorts of problems in particular. We're calling this routine forkref, and it requires that I be in the range 1 to 5. So we can go to forkref. Actually, forkref is a local procedure right here. And it's using I as an index into this forks procedure. And forks is a array. There's our array of 5 forks. And if we index into that array, we'd better use a number between 1 and 5. And so CodePeer is checking to be sure that all of our indices are in that range. Let's turn off the window right now, but right here we see we're using a 0 and a 2. That's fine, but the 0 is the one that's out of bounds. So we had array out of bounds on this one, and we had a couple other problems. But the general idea is that it highlights these things. We can click on them, and we can read the message, and then, presuming we understand the nature of the program, we say, oh, that should have been a 1. So let's change this to a 1. And now let's reanalyze and see if we get rid of at least that one problem. Okay, so let's go back to our test dining philosophers. Aha! This is now no longer a problem. So we have successfully solved one problem. And I'm going to undo that change just so we don't end up with the test case doing something different. One thing that is a nice new feature of CodePeer that we haven't necessarily demonstrated before is it now allows you to hover over an expression such as forkref counter +1 or forkref counter. And as I mentioned, it determines what are the possible values of every expression at every place in the program. Well, now we actually tell the programmer when they hover over it, what are the possible values? So we're telling you that this forkref counter is in the range 1 to 10, and here it's this expression is also in the range 1 to 10. And what was forkref counter initialized to? Well, let's scroll up a little bit here. It was initialized to 1, and so the first time around this is a 1, and it's guaranteed to be in the range 0 to 10. So we know that whenever we add 1 to it, we're now in the range 1 to 10. And we don't necessarily know in this piece of code what its value is before we call it, but we know overall the range will always be 1 to 10. So if you have a question for why is CodePeer complaining about something, you can hover over it, and it can give you its idea of what are the possible values. Okay, so now let's look at some race conditions. I promised you that I'd demonstrate some race conditions. So in the dining philosophers code, we have a number of race conditions. In fact, we have a whole race conditions report. Let's start there. It's a little bit better way to think about it. So this identified 2 objects that have a danger of race conditions, still eating and counter. And let's look at one of these. So for example, let's look at still eating. And that gets us down to this check here, which we'll click on. And still eating is a global variable, which is always something to worry about when you start thinking about multi-threading, multitasking. Global variables are generally evil, as we were told in our first class in programming, or at least in software engineering. Here we have a global variable, totally unprotected, and we're bumping this count of how many philosophers are still eating, or we're decrementing it by 1 each time around this loop when just before the task goes to sleep. So that's a little bit of a concern. Well, there are various ways to fix this. The best way is to create a protected object and have a decrement function, or decrement procedure, and that can do this in a safe way. But another way to do this sort of thing, to eliminate at least the low-level race condition, is simply to mark this object, still eating, as being atomic. And in the latest version of Ada, we can do that quite nicely by just saying with atomic. So if we rerun this, it should no longer complain about that particular race condition. Now, as we know, this is really not the right solution. It'd be better to turn this into a protected object. But as far as a low-level data race, we're now eliminating it, because by marking this as atomic, we're saying we want every reference to it to be a uninterruptible load or uninterruptible store. So now we are at least not creating an erroneous program. In Ada, it's erroneous if two tasks reference a non-atomic variable or a non-protected object simultaneously. So we're no longer erroneous. I would say we haven't really solved the problem because there still is a higher level race condition. And that's an interesting thing about race conditions. There's a low level notion of a data race where you just have two tasks actually trying to read or write the same variable at the same time. And there's a higher level thing where really our goal here was to subtract one. But suppose we had two threads running simultaneously. Well, they might both read the old value. They'd each subtract one from the old value. And then they'd both store the same new value into this still eating. And we would not have decremented by 2, which was the goal. Instead, we've decremented by a total of only 1, even though 2 tasks executed this line of code. So the fix we made is really not ideal, but it does illustrate that you can eliminate a low-level race condition by simply marking something as atomic. I'm going to put it back again just to be sure that we don't forget to undo the changes we made.